Another important model for the estimation of distributed lag model is the stock adjustment model or partial adjustment model, and it was put forward by Mark Nerlow. And this model can be explained as follows. And for the explanation, consider the flexible accelerator model of economic theory. And the flexible accelerator model of economic theory assumes that there is an equilibrium, optimal, desired, or long-run amount of capital stock needed to produce a given level of output under a given state of technology and rate of interest. That is, a flexible accelerator model of economic theory states that in order to produce a given level of output, given the state of technology and the rate of interest, or keeping these factors constant, it requires an equilibrium or optimal or desired or longer amount of capital stock. And this desired level of capital stock, the desired stock of capital, is denoted as YT star and is a linear function of output X, and which can be specified as follows, that is YT star equal to beta 0 plus beta 1 xt plus ut. Since the desired level of capital is not directly observable, that is YT star is not directly observable, Nerlow, that is Mark Nerlow, postulated the following hypothesis, which is known as the partial adjustment or the stock adjustment model. That is, this desired stock of capital is needed to produce a given level of output. Since this desired stock of capital is not observable, he defined it in the following way. That is, this definition, that is, he defined the desired stock of capital as YT minus 1, that equal to dou YT star minus YT minus 1. This is the partial adjustment or stock adjustment hypothesis. This hypothesis is known as the stock adjustment hypothesis or partial adjustment hypothesis. That is YT minus 1 equal to dou YT star minus YT minus 1, where dou, which lies between 0 to 1, and this dou is known as the coefficient of adjustment, where YT minus 1, that is this equal to the actual change, and YT star minus YT minus 1, that is equal to the desired change. This YT minus 1 is the investment, or the above equation, this equation, that is YT minus 1 is the actual change in stock of capital. This is the desired change in capital. That is, actual stock in capital is known as the difference between the current and the previous period stock of capital is known as the investment. Therefore, this equation can be written as investment IT equal to dou YT star minus YT minus 1, where IT is the investment in period T. This equation to postulate that actual change in capital stock in any given period is some fraction of desired change for that period. That is, this definition states that actual change is a function, or it is proportional to dou of the desired change in capital. If dou equal to 1, it means that actual stock of capital equal to if this is 1, then YT minus 1 or IT investment equal to the desired stock of capital. However, if dou equal to 0, it means that nothing changes, since actual stock at time t is the same as that observed in the previous period. Typically, dou is expected to lie between these two extremes, since the adjustment to the desired stock of capital is likely to be incomplete because of rigidity, inertia, contractual obligations, etc. Hence the name partial adjustment model. We cannot, or this why partial, the term partial means that it is the change in stock of capital won't be full. It will be partial or it will be incomplete due to the rigidity, inertia, contractual obligations, etc. The adjustment mechanism given in equation 2 can be alternatively written as YT equal to dou YT star plus 1 minus dou YT minus 1. This is nothing but we made on the left hand side and brought this one to this side. That is YT equal to, then multiply this one, YT equal to, multiply this term by dou, that is dou YT minus dou YT minus 1, that is remove the bracket, then bring this YT minus 1 to this side, then it will be equal to YT plus YT minus 1, that is this can be written as dou YT minus 1 plus 1 minus dou into yt minus 1. That is given here. That is yt equal to dou yt star plus 1 minus dou into yt minus. It shows that the observed capital stock at time t is a weighted average of the desired stock of capital at that time and the stock of capital existing in the previous period, and the weights being dou and 1 minus dou. That is, actual stock of capital depends upon the desired stock of capital and the stock of capital in the previous period by a weighted average of dou and yt minus 1 by 1 minus dou. This is this definition. And showing that observed capital stock at time t is a weighted average of desired stock of capital at that time t and the capital stock existing in the previous period. Substitute the equation 1 into equation. That is, equation 1 is yt star equal to beta 0 plus beta 1 xt plus ut. Then substitute this. This is equation 1. This is equation number 4. That is, substitute equation 1 into 4. That is, replace this yt star by this yt star. That is equal to beta 0 plus beta 1 xt plus ut. That equals yt equal to dou yt star equal to beta 0 plus beta 1 xt plus ut plus 1 minus dou yt minus the other things remaining the same. Then remove the bracket. Dou beta 0 plus dou beta 1 xt plus 1 minus dou yt minus 1 plus dou ut. This is only a simple arrangement. This model is known as the partial adjustment model or PAM. That is, what we have done is that define this model. That is, desired stock of capital is a positive function of the output. Then define the desired stock of capital. From that, define the partial adjustment hypothesis. From that, derive this equation, that is desired stock of capital, actual stock of capital, if weighted average of the desired stock and the stock of capital in the previous period. Then replace this by the first equation. Then what we will get is known as the partial adjustment model. The equation 1 is known as the long run or equilibrium demand stock for demand for capital stock. And 5 is called the short run demand function for the capital stock, since in the short run, the existing capital stock may not necessarily be equal to its long run. Once we estimate short run function and obtain the estimates of the adjustment coefficient dou from the coefficient of yt minus 1, we can easily derive the long run function by simply dividing dou beta 0 by dou beta 1 by dou and omitting the lagged by term, which will then give the equation 1. Geometrically, the partial adjustment model can be shown as in figure. In this figure, y star is this is the y star, this is the desired stock of capital, which it is not observable, and y1 is the current actual stock of capital. For the illustrative purpose, it is assumed that dou equal to 0.5. What this 0.5 means is that the firm plans to close half the gap between the actual and desired stock of capital each period. That is the meaning of dou equal to 5. That is, it desires to close the gap between, there will be a gap between the actual and the desired. And if it is 0.5, that is, the firm desires to close 50% of this gap in each period. Thus, in the first period, it moves to y2, it is given here, with investment equal to y2 minus y1, which in turn equal to half of this y1, y star minus y1. In each subsequent period, it closes half the gap between the capital stock and the beginning and at the beginning of the period and at the beginning of the period and the desired stock of capital. That is, in each period, it this here half, then the remaining portion half, then another half, like that. It closes the gap between the actual and the desired stock of capital. The partial adjustment model resembles both the chaotic and adaptive expectation model in that it is also auto-regressive. That is, this is the partial adjustment model. This is also auto-regressive since it incorporates the lagged value of the dependent variable. Now, a combination of adaptive and partial adjustment model is given here. Here, yt star equal to beta 0 plus beta 1 xt star plus ut. where yt star is the desired stock of capital and xt star is the expected level of output. Since both yt star and xt star is not directly observable, one could use the partial adjustment mechanism for yt star and adaptive expectation model for xt star to derive the following mechanism. This is a combination of the adaptive expectation model. This is the adaptive expectation model. Then this is the partial adjustment model. That is, here we can see the coefficients of both adaptive expectation, the partial adjustment model, and adaptive expectation, that is dou and gamma, and which can be written as alpha 0 plus alpha. By replacing or by symbol manipulation, we can see that alpha 0 plus alpha 1 xt, this is replaced of alpha 2 yt minus 1, this one, alpha 3 yt minus 2 plus vt, this term. We simply combined both these terms. An application of this equation is the Friedman hypothesis, which states that permanent or long-run consumption is a function of permanent or long-run income. Estimation of autoregressive model. That we know that all the models that we have explained, correct model, adaptive expectation, partial adjustment model, all these models are autoregressive. The correct model is that yt equal to alpha into 1 minus lambda plus beta 0 xt plus lambda yt minus 1 plus ut minus lambda ut minus 1. Adaptive expectation model is also like this: gamma beta 0 plus gamma beta 1 xt plus 1 minus gamma yt minus 1 plus ut minus 1 minus gamma ut minus 1. And partial adjustment model is yt equal to dou beta 0 plus dou beta 1 xt plus 1 minus dou yt minus 1 plus dou ut. All these models have the same common form, that is yt equal to alpha 0, that is beta 0 xt, gamma 0 xt, sorry, alpha 1 minus lambda, gamma beta 0, lambda beta 0, etc. Alpha 0 plus alpha 1 xt, everything has that, and alpha 2 yt minus 1 plus vt. That is, they are all autoregressive in nature. And the next important model for the estimation of distributed lag model is the Allman's approach to the distributed lag model, or Allman's or polynomial distributed lag model. This theory or his estimation procedure can be explained as follows. That is, we know that correct distributed lag model is quite widely used or extensively used. This correct model is based on the assumption that beta coefficient declines geometrically as lag. This assumption may be too restrictive, and consider, for example, the following figure. In figure A, it is assumed that beta increases first and then decreases. But in the correct model, he assumes that it declines geometrically. But there may be situations in which there may be movements like this, that is, like this, or like this. We know so many situations in which the economic variable exhibits pattern like this. In this situation, the correct model is not applicable, and in order to explain or in order to show the pattern of movement in such variable, we uses or Allman has proposed another important alternative approaches for the estimation of distributed lag model. Let us consider a finite lag distributed lag model. Earlier we considered the infinite lag model. Here we are considering the finite lag model. That is, Allman's model is based on the finite lag model, that is yt equal to alpha plus beta 0 xt plus beta 1 xt minus 1 plus beta 2 xt minus 2 plus beta k xt minus k plus ut, that is, the lag is given, which may be written more compactly as alpha plus sigma of I equal to 0 to beta I xt minus I plus ut. That is, we can write down this equation in a very compact form, that is yt. It is equal to alpha 0 plus, here it is equal to, if alpha I equal to 0, then xt minus 0 xt minus 0, that is beta 0 xt. If I equal to 1, that is beta 1 xt minus 1. If I equal to 2, beta 2 xt minus 2, etc. This up to we can write, if I equal to k, then beta k xt minus k plus ut. That is, we can write down this equation in a very compact form as yt equal to alpha plus sigma of I equal to 0 to k, since the reason is that here we are using the finite lag models, and this beta I is based on certain assumptions, and this assumption, he explained this model using the Weierstrass theorem, which is used in mathematical, or which is a theorem of mathematics, And he assumes that beta I can be approximated by a suitable degree of polynomial. If the lag scheme shown in figure A applies, we can write the above equation as beta I equal to a0 plus a1I plus a2I square. That is, if this is the pattern, then using the Weierstrass theorem, we can write down this in the form of the polynomial, or we can define beta I as follows, that is beta I equal to a0 plus a1I plus a2I square. It is a quadratic or second degree polynomial in I. Or if beta follows the pattern in figure C, that is if it is like this, then we can write down beta I or the function as beta I equal to a0 plus a1I plus a2I2 plus a3I3, a2I square plus a3I3, which is a third degree polynomial. Or we can write down the equation more generally as beta I equal to a0 plus a1I plus a2I square plus am up to the nth degree polynomial. And the elements approach can be explained as follows, and for that he used the second degree polynomial, that is if the shape is like this, the compact form is yt equal to alpha plus beta. The compact form is yt equal to alpha plus sigma of I equal to 0 to beta I xt minus I plus ut. And in this case, he defined beta I as beta I equal to a0 plus a1I plus a2I square. Here, the degree of polynomial depends upon the number of curvature. If the number of turning point is only one, if we have only one turning point, then the degree will be 2. In figure C, we have one more turning point, that is here and here, then the degree of polynomial will be 3. That is 1 turning point plus 1 will be the degree of polynomial, is the theorem used, or is the explanation given by the Weierstrass theorem, and he applied it into this equation. Now replace this beta I using this one. Then what we'll get, yt equal to alpha plus sigma of I equal to k to a0 plus, substitute simply this beta I by this one, a0 plus a1I plus a2I square plus xt minus 1 plus ut. Then remove the bracket, that is alpha plus a0 sigma of xt minus 1 plus a1 sigma of this one I equal to 0 to k to I xt minus 1, then a2 sigma of I equal to 0 to k I square yt xt minus 1 plus ut. Then replace this equation using these notations, that is this term as z0t, this term as z1t, this term as z2t. Then this equation can be written as yt equal to alpha plus a0 z02 a1 z1t plus a2 z2t plus ut. That is, in element scheme, y is regressed on the constructed variable set, not on the original x variable. That is, here we are regressing yt on the constructed variable, and the equation, so this equation can be estimated using the OLS procedure. That is, the estimates of alpha and ai thus obtained will have the desired statistical properties provided stochastic disturbance term satisfies the assumption of classical linear regression model. Here there will be no correlation between the yt minus 1 and the disturbance term, which is one of the important problem of the correct model. Once A's are estimated, the original betas can be constructed from this one. That is, we estimate this model, we will get Z0t, Z1t, Z2t. From this Z0t, Z1t, Z2, from this A0, A1, A2, we need to calculate the beta I, or the beta 0 plus beta 1, beta 0, beta 1, beta 2, etc. This is also defined like this: beta 0 cap equal to A0 cap, beta 1 cap equal to A0 cap plus A1 cap plus A2 cap. For this second degree polynomial model, B2 cap equal to A0 cap plus 2 A1 cap plus 4 A2 cap, B3 cap equal to A0 cap plus 3 A1 cap plus 9 A2, that is square of this one. That is, beta k cap can be defined as A0 cap, then k A1 cap. Here this is 3, this is 3, if this is 2, this is 2. That is If this is k, then k a1 cap. Then if this is 3, this is 9. A2 cap is square. If this is 2, this A2, the coefficient of A2 cap is square of this one. Like that, this will be equal to k square A2. Like that, we can derive the value of beta 0 cap, beta 1 cap, beta cap up to beta k. What are the or it faces certain practical problems, and these practical problems are given here. The maximum length of lag must be specified in advance. That means this is a finite lag model. Therefore, we want to know the number of lag. Then the second important problem faced by the Almond's model is that we want to know the degree of polynomial. That is, the degree of polynomial generally is that it will be equal to 1 plus the number of turning points. And for the third degree polynomial, the model will be like this. That is yt equal to alpha plus I0 plus 0 z0t plus a1 z1t plus a2 z2t plus a3 z3t plus ut. Once m1k are specified, set can be really constructed as follows: z0t equal to sigma of I equal to 0 to 5. If m equal to 2 and k equal to 5, that is 0 to 5, that is xt minus 1, xt plus xt minus 1 plus xt minus 2 plus xt minus up to 5. Then z1t equal to I xt minus 1, that is xt minus 1, 2 xt minus 2, 3, 4 xt minus 5, xt minus 2. Then if it is z2t, this will be equal to I square, that is xt minus 1, 4 xt minus 2, 9 xt minus 3, 16 xt minus 4, 25 xt minus 5. If the number is 3, then this will be equal to I cube xt minus 1. Like that, we can construct the model.